Computing environments are strictly discrete. At their core, processors operate in stepped intervals, managing data in distinct arrays, individual pixels, and rigid binary states. But the physical world is not discrete. It is a continuous, unbroken flow of matter and energy, like a glacier steadily carving a valley. To simulate this fluid reality inside a rigid, discrete computer system, engineers require a mathematical bridge to translate continuous movement into calculable data. Calculus provides two primary mechanisms for this. The first is differentiation, which calculates the precise rate of change of a system at one specific frozen moment in time. The second mechanism is integration. It is the exact mathematical reverse of differentiation. Instead of isolating a single moment of change, integration calculates the continuous accumulation of values over a defined period. This is the integral symbol. It functions as an aggregator, capturing an infinite series of continuous, infinitesimal slices and summing them together into a single measurement. We can trace exactly how this mechanism works by moving from generalized abstract models to precisely bounded geometric areas, and finally examining the specific algorithms used to dismantle complex functions. These are the mechanical steps required to build physics engines, computer graphics pipelines, and machine learning models. Without the logic of integration, a discrete machine could never accurately model the accumulated reality of the physical world. Integration operates in two distinct modes. It can represent an abstract family of functions, or it can provide a precise empirical measurement. This chart shows the function f of x equals 2x plotted on a coordinate plane. When we write the indefinite integral of 2x with respect to x, we are looking for a generalized formula for accumulation. Reversing the rule of differentiation tells us the base answer is x squared plus c. That c represents the constant of integration. Because the derivative of any constant is 0, there are infinitely many starting positions that could yield our original function. This constant generates a complete family of parallel parabolas shifting along the y-axis. We use this indefinite general form to build theoretical models of systems where the exact starting conditions remain unknown. However, when we need a concrete measurement, we apply specific numerical bounds. This collapses our abstract model into a definite integral. By adding a lower bound of 0 and an upper bound of 2, we instruct the equation to calculate the exact accumulation strictly between those two coordinates. Evaluating this requires applying the upper bound and the lower bound to our antiderivative, then subtracting the lower result from the upper result. The calculation yields a final numerical value of 2. Geometrically, this number is the precise area under the curve between 0 and 2. In a computational context, calculating the area under a curve is functionally identical to calculating total data accumulation over a specified time or distance. Indefinite integrals construct the theoretical framework of a system, while definite integrals extract the hard, bounded data required for operations like continuous signal processing. Real-world computing systems rarely model simple polynomials. They manage interwoven behaviors that standard integration rules cannot resolve directly. These behaviors often take the form of composite functions, where one mathematical function is entirely nested inside another. To integrate these, we use the substitution method. This is a systematic algorithm designed to reverse the chain rule of differentiation. Consider this complex target equation: the integral of 2x multiplied by the nested function x squared plus 1 cubed. We cannot integrate this structure as written. First, we identify the problematic inner function, x squared plus 1, and its derivative component sitting outside it, 2x. We define a new temporary variable, u, to represent that nested inner function. By substituting u into the equation, the complex nested structure completely collapses into a foundational form, the integral of u cubed, which is trivial to solve. Compilers and computational algebra systems rely on this exact structural simplification to process nested logic efficiently. Substitution operates as an essential algorithmic process for untangling dependent variables inside continuous simulations. Another mathematical roadblock occurs when two entirely different functions are multiplied together, rather than nested. To resolve multiplied functions, we apply a structural method called integration by parts, which reverses the product rule. The formal rule states that the integral of u with respect to v is equal to u times v minus the integral of v with respect to u. The strategic intent here is not to solve the equation in one step, but to trade an impossible integral on the left side for a completely new, manageable integral on the right side. We can apply this to the integral of x times e to the power of x. By systematically assigning the x component to the variable u and the exponential component to the variable dv, we mathematically dismantle the multiplied terms. Mastering this specific algebraic restructuring is a baseline requirement for optimizing the complex probability distributions inside machine learning models. Substitution and integration by parts function as programmable algorithms. They prove that advanced integration is achieved through the systematic deconstruction of complexity. Beyond abstract algebraic manipulation, these tools allow us to measure intersecting systems in geometric reality. This graph displays a parabolic curve intersecting directly with a straight diagonal line. To find the precise area trapped between them, we integrate the function representing the upper boundary minus the function representing the lower boundary. The exact coordinates where these two functions intersect serve as the specific numerical limits for this definite integral. Calculating these bounded regions defined by intersecting boundaries is the core mathematical engine driving computer graphics rendering and complex data visualization. Integration provides the rigorous mathematical mechanism needed to calculate continuous accumulation. Indefinite integrals construct generalized structural models, while definite integrals extract the exact numerical values dictated by physical boundaries. When those systems scale in complexity, algorithms like substitution and integration by parts algebraically dismantle unmanageable functions into solvable pieces. These mathematical rules dictate how software accurately renders the continuous, fluid dynamics of airflow and overlapping physical shapes. By executing the architecture of integration, engineers successfully bridge the gap between strict, discrete binary code and the unbroken, accumulating reality of the physical world.